All right, well, now that we've learned how to take derivatives in a somewhat easier way, in other words, we now have a collection of rules which helps us avoid having to go through and always argue with limits, well, now we should start exploring a little bit more about derivatives. And one of the things we're going to talk about is higher order derivatives. In other words, well, we took a derivative once, but what about second derivative? All right, we'll get into that. And of course, we'll start dabbling in some applications. But let's start with higher order derivatives. All right. So the basic philosophy is we can start with any function we want and we can take its derivative. If you remember the picture we had from a few sessions ago, we said, hey, here's this sort of machine where it says if I have a function, I can plug any function I want into this machine, f of x, and it's called the derivative machine. And what will happen is out of this will come something called f prime of x. It's a new function. So what does it mean to take another derivative? Well, the idea is to say, hey, let us start with the derivative that we have, and let's feed that back into the machine. And if we feed the first derivative in, well, that'll be the derivative of the derivative. And out comes a new function. Well, we need to give it a new name. So we call it the second derivative. And of course, you can call this, we normally write this to f with two primes. So if you think of prime as indicating one derivative, two primes indicate, hey, two derivatives have happened. In other words, we've fed it through the machine twice. And of course, if we've done it twice, why stop there? We can feed it again and again and again. And of course, that's how you make the sausage, right? Just keep putting it back in and back in and back in. So the moral here is that we can take derivatives of derivatives. So we want to talk a little bit about this. Now, the basic thing we want to talk about for right now is what's the notation? The actual processes are the same, because if I know how to take the first derivative, then I can take any number of derivatives. I just keep applying the rules again and again and again. There's no need for new rules. It's just how many times do we need to take derivatives. So, notationally, if I have the function, I'll call it y or f of x, then here's some common notations you'll see for derivatives. The prime is very common, so y prime or f prime or dy dx. And whenever you see a d, we should always think of that as, oh, d means a small change in, or how one thing is changing with respect to another thing. Because derivatives measure rates of change. So dy dx, how is y changing as I'm changing x? Now, second derivative. Okay, well, two primes, prime prime. Well, that just indicates you did it twice. Or f double prime. Now, it gets a little bit more interesting with the notation if you use the d notation. By the way, if you're wondering, is it called d notation? It's actually called differential notation. So if you ever hear that phrase, differential, that's what it's referring to. So how do you mark it? Well, it's d squared y dx squared. And we'll get a little bit into that in just a few minutes about why, even though it seems peculiar at first, it actually makes sense. Now, in general, we can keep going. So we can talk about the nth derivative. So we can take any number of derivatives. And you might wonder, do we really need to do that? And the answer is yes. Indeed, when we hit calculus 2, we're going to take all the derivatives. Infinitely many in some sense. So we got to be ready for that. So the nth derivative, well, notice that we're going to give up on the primes. Why give up on the primes? Well, it's very cumbersome to keep writing primes. And so after about maybe the third or the fourth derivative, we kick and we say, we're not going to write primes anymore. So why? Well, look at this. Here, I have some number of primes. Now, if you're very patient, and if I did it right, okay, that's two challenging things. There are 17. So that's the 17th derivative. At a glance, it's not easy to tell that's true. But if I switch and say, oh, if I have 17 up here, then it's like, okay, I can see you did something 17 times, and that means the 17th derivative. So So that's how we're going to represent a higher order derivative. So again, if you see like y to something, that's the nth derivative of y, f, nth derivative, all right. And in the d notation, dn to the y, dx to the n. All right, good. Now, a little bit of notational note here. So you'll notice that there's these little things here called parentheses. Now, if you know me, you know I like parentheses. I think they're a very useful thing to use because parentheses are a wonderful way to make sure that we haven't forgotten anything and to keep track of what's going on. So we want to use parentheses. Oops, I highlighted the wrong parentheses. These parentheses up here. Now, why do we put parentheses around those? Well, it is because there's a small technical thing which, depending on where you go, there's another notation. So if you see, sometimes you'll see f like 2 of x, and then versus f parentheses 2 of x, where both can be used. And what do they mean? So this notation we've talked about, that's our second derivative. So that's one notation. Now f2 of x, here is what it commonly gets interpreted as. Depending upon, when I say commonly, of course it varies depending upon what part of math you're in. This is an iterated function evaluation. So in other words, this is interpreted as f of x, which is different from the second derivative. So they want to have ways to have both of these types of operations because both of them show up in various places in mathematics. Now you might think for a second, all right, hold on. I happen to know something. Oh, I love this. I love it when people know stuff. It's cool. It's cool. I took trig. Oh, me too. I love it. It's great stuff. I love trig. And I know that in trig, they often write sine squared of x in this way, as meaning sine of x quantity squared. So wait a second, isn't that breaking the rule? And the answer is, it does break the rule. And so you might be wondering, well, why does it break the rule? Why does the trig get off the hook? And well, here's the thing is, I think the problem is that trigonometry is so old that it sort of predates good notation. And so there was sort of bad notation being used at the beginning. And then people got so used to it, they're like, we're sticking with our bad notation. You can't make us change, even though we know it's bad to begin with. And there's, we'll get into some places where trigonometry notation can be a little bit dangerous. So, but that's to come. That's to come. All right. Now you might wonder, by the way, is there really ever a part of math where they look at things where there's a function plugged back into itself? And there is. This is called iterated functions. You iterate plugging it in. And if you've ever heard of things like chaos or fractals, that's where that shows up. All right. We're getting distracted here. We need to get back on track because we're here to talk about derivatives. And so now we have our higher order derivatives. The next thing we want to talk about is understanding the units of derivatives. Why do we want to do that? Well, in some sense, it's going to help us understand our choice of notation, but it's also helpful to understand how derivatives function. All right, so suppose I have some function, and I want to take its derivative. So I have y is f of x. Now, if you look at the definition of the derivative, what is it? Well, you say f prime of x is a limit as z goes to x of f of z minus f of x over z minus x. Now I'm writing it in this format to help remember what things are. So the numerator here, that looks at the change in the output. And the denominator looks at the change in the input. Oftentimes if we write the denominator as h, it's easy to forget that it really corresponds to, hey, something downstairs is changing, that's our input changing. Because we think, oh, it's just a number. But it's really about a change in our input. And so we say, okay, so if we think about what's happening, we say, all right, it's the units of y, or in other words, it's the unit of our function over the units of our input. So that's how we can think of what happens when we talk about our function. So we can make a function really depend on anything we want. So we could say, what could we do? Well, we could make a new function. We could say, well, f of, say, u. Well, that's not necessarily the best thing because you might misread that as not f of u, but you might just say f. Well, I can't even say it out loud. This is a PG calculus channel. But all right. Well, what is u? U, you could say, is, say, gallons. So I have a car, and this is like how many gallons are being put in. And the output of this is how many miles I travel. And now I could say, if this is my function, well, my function is a measurement of miles. That's the output. What would be the derivative, f prime of u? Well, if I think about it, what do I have? The output would be miles. So this is the output of the function. And the input is gallons. So the original function has its units here. That's units are miles here. So this is the units of the function. This is the miles per gallon is the derivative of units. So that's how units can work. Okay, now let's start getting to the higher order derivatives. So what is the derivative of the derivative, the second derivative? Well, that we can represent in the following way. So this is our notation, remember that? d2y dx squared, which is d dx r over of dy dx, so right? So this is, whenever you see that d dx, that means, hey, we're about to take a derivative, and take a derivative of what? Of this thing. Well, what is that thing? It's the derivative. So we can see it, we can read it off. Take a derivative of the derivative. And like, oh yeah, that's the second derivative. That's what it means. All right, so that's the derivative. Of course, f prime of x, that's just another way of saying the derivative. So it's the limit as z goes to x of f prime of z minus f prime of x over z minus x. So far, no surprises. So now, what are the units? Okay, if we think about what's going on here, up here we have the derivative. So the units upstairs are the units of f prime of x. The units downstairs, that's the units of our input. It's the units of x. So now we're like, okay, cool. What do we know about f prime of x? Well, that's the units of y over the units of x. That's what we said. Divided by the units of x, which becomes the units of y over the units of x squared. We're going to talk a little bit about an application in a few minutes which deals with velocity. But sometimes we talk about like things like acceleration, like gravity, and you hear meters per second squared. And you're like, what is a square second? I've never seen a square second. Well, it's not really a square second. What's happening, it's the meters per second per second. See, there's that sort of meters per second per second. And so that's how you end up with meters per second squared. Now, this keeps going. And what do you end up with? You say that the nth derivative of the function, so dny over dx, and that's the nth derivative, becomes the units of y over the units of x to the n. See, you can see it. First derivative, units of y, units of x. Second derivative, units of y, units of x squared. Nth derivative, units of y, units of x to the n. Now here's why I love this notation. It's so suggestive. If I'm looking at this, I want to ask, suppose I see this expression. What are the units? Well, I say, hey, what are the units of y? Because I just see a single y. And then I say, well, wait, what are the units of x to the n? Because see how it's like x to the nth power? So that's how we get the downstairs. It matches. You raise this to the nth power. You don't raise that. It's just the original units themselves. And so it's beautiful. It's beautiful. It's like calculus is set up in such a way that things will work nicely. It's almost like we want things to work nicely. Spoiler alert, we do. We do want things to work nicely. All right. So that's higher order derivatives. And we're going to get some practice taking higher order derivatives. One thing we'll also do is start looking at what happens when you take derivatives. When you take lots of derivatives, you want to start looking for certain patterns. And we'll see that certain functions behave in certain ways, in really very predictable ways. It's a good chance for us to start saying, hey, I can spot patterns. Now, we're not done yet for today because there's some other topic we want to talk about. We want to get into a little bit of applications and understanding derivatives. Now remember, derivatives are all about measuring change. So we're going to talk about ways that understanding change can help us. And there's lots of ways that derivatives can show up as change. So we can ask, how does our output change as we change our input? Now we're going to sort of delve into two applications. Now the first one is going to be really familiar. It's going to be a little bit of physics. And there's a lot of overlap between physics and mathematics and calculus in particular. It's not too surprising. In the history of mathematics, most mathematicians were what we call applied mathematicians. In other words, they were interested in saying, hey, I have this real world problem. Let me try to use the tools of mathematics to answer it. And as a consequence, a lot of the really good people who were good at math also were good at physics, which is in some sense an application of math to the real world. Modern day mathematicians, they're sort of a mixture. There are still mathematicians who are very much interested in the applied side of mathematics. There are also mathematicians who are like, I love math for its pure beauty. Of course, both mathematicians are wonderful people, and you should, hang out with both kinds. They have lots of good things to say. All right, back to the story. Physics. So we're going to start very, very simply, which is to say, let's imagine that we have a line. So we're going to imagine ourselves on the number line. And so we also think of it really as an oriented number line. So you can head off, infinity is in one direction and minus infinity in the other direction. So there's our line. And now what we'll do is we have this little tiny particle here. Now at any given time t, that particle is somewhere on the line. Now what can happen is it can move back and forth. You might think this is oversimplified for a couple of different reasons. First off, most things don't live in a one-dimensional world. Well, we'll start working our way up to multiple dimensions. In fact, there's a beautiful class, multivariable calculus, where we really go and say, hey, here's how you do everything in multiple dimensions. And the secret is you just have to figure out how to do things in one dimension and then just do it multiple times. So, all right, so let's just accept that. You might say another thing is, well, most things aren't particles. They're like large bodies, they're huge. But in most applications, you can actually say it suffices to represent things as single points. Like when you're modeling a solar system, you don't have to model every single atom. You can say, look, let's just think of the sun, which is this really big object, as a single, very heavy point. And here's this planet, also a very single, not quite as heavy point, and see how they interact. So it's okay to think of things as particles. So what do we have? Well, the particle is moving around. So what we'll do is we'll talk about S of t. So S of t is the position. And now we can start saying, all right, we want to understand the change. How is this particle changing with time? So we have some particular names to these phenomenons. The first thing we can ask is, what's the velocity? Now, the velocity is really trying to get into the question, how does position change? Whenever you see a question, how does something change? What you're really asking is, what's the derivative? So when we talk about how position changing, that's asking, what can we say about our S prime of t? All right, so what are our units? Well, it depends. If we think about here, position, let's suppose we assign this to be meters. And suppose time, let's say we assign those to be seconds, then what are our units for velocity? It's meters per second, right? Because you take your units of your S divided by your units of t. Okay. Now, there's a related idea called speed. Now, what's the difference between velocity and speed? Well, speed is always a non-negative value. So in some sense, it's how quickly your position is changing, but it's ignoring which direction the change is occurring. So the difference is, in some sense, the speed here, when we get speed, you ignore orientation. Or another way to say orientation is you ignore direction. And this is sort of an important thing. Mathematics, and in particular calculus, is very much an oriented subject. In other words, we're moving left or right. Orientation matters a lot. So it's important to understand our orientation. So when we talk about things like positive and negative, what we're really talking about is let's orient ourselves on this line. And so it's important to keep track. If you remove orientation, a lot of calculus starts to break down. And so in some sense, the velocity feeds us a lot more information than just what speed does. But it's good to understand both. Now, if velocity is how position changes, we can now answer, or rather ask the question, how does velocity change? And that has a particular name. That's called acceleration. So when we talk about acceleration, acceleration is our change in velocity. So if we think about what that represents, if I want to understand how something changes, I say, okay, if I want to understand change, I take a derivative. So it's the derivative of velocity. Well, wait a second. The derivative of velocity is the derivative of position. And so we have the second derivative of position. So that's why we talk about the second derivative gives us acceleration. Now let's talk about the units. So it's the second derivative. So if I think about the units, I say, hey, it's the units of s, which is meters, and then divide by the units of t squared, because there were two derivatives. Meters per second squared. Good. Okay, there is some notes here, and I think it's important to understand just because it's good to start building up our understanding. So when we think about a particle, one of the things we can talk about is its movement. So that's given by the velocity. If a particle is at rest, so in other words, it's doing what this is doing right now, not moving, then the velocity is zero. It's not moving left or right, so we say the velocity is zero and the speed is zero. Now we have to start making a decision. How do we distinguish between moving left and moving right? So the way we do that is we think about the sign of the velocity. So if I'm moving to the right, what does that mean? It means my position is increasing. So as time is moving forward, position is also going up, so that there's this nice correlation occurring. If I'm moving to the left, that says that as time is increasing, position is decreasing, so that there's sort of an anti-correlation or a negative correlation. So we can now say positive velocity moves to the right, and negative velocity moves to the left. So this is why it's nice to have the sign of velocity. It's giving us information, not just at the speed at which a particle is moving, but the direction at which a particle is moving as well. Okay, good. So that's a good reason to keep track of your sign. And by the way, orientation matters a lot. It really helps us to break symmetry. And that's going to be a really big topic, especially once we hit Calculus 3. And I know we're just starting in Calculus 1, but we can look forward to all the good days that are ahead, right? Of course we can. All right, one more topic. And we're going to do a little bit of economics. Economics. Some people say it's the dismal science, but it's not so bad. It's actually a beautiful topic. You may not know this about me. I actually have a degree in economics. I also studied mathematics as well. In fact, that's my first love. But economics is a really interesting topic. And nowadays, there's a lot more mathematics happening in economics than there used to be. See, it used to be the case 50, 60 years ago, if you wanted to get a degree in economics, you had to draw a picture and tell a good story. Now, you actually have to get the math. And so that's actually happening a lot. The world is becoming more and more quantitative, so we want to make sure we're good at doing math. And by the way, another reason why I love economics, it's kind of a genetic thing. My dad was a professor of economics for many decades. And I actually have an older brother who has a PhD in economics. So yeah, I have a soft spot in my heart for economics. We're just going to do a little tiny bit. So suppose you're making a decision about whether or not to make more product. Okay, well that's a compelling thing. And in essence, the question is, when should we make more and when should we make less? And you might hear something called margin. Well, margin means the edge, the very last product. And the question is it to our benefit to make another one, or is it not to our benefit to make another one? So how do we figure this out? Well, what we can do is we can say, let's look at what would happen if we made one more. So we're going to think of Q as how many things are currently being made. So now I have a quantity Q, and I have some functions, my cost function and my revenue function. So cost, that's how much money it costs me to make one more product. Revenue is how much money I earn for making one more product. So now what's the marginal cost? Well, the marginal cost says how much does it cost you to make the next one? So you can say, okay, take the cost of making one more, subtract the cost of just the current quantity, and divide by 1. Now you'll see there's this squiggly C prime of Q. Where is that coming from? Well, remember, what is C prime of Q? This is the limit as h goes to 0 of C of Q plus h minus C of Q all over h. So the idea here is you can say, well, I want to take the limit as h gets very small. Now, here, this is what happens when you plug in h equals 1. You might say, 1 is not very small. And you're right. In context, though, if Q is, say, 1,000,000, then relatively speaking, 1 is small. So it's sort of a decent stand-in for most cases. So we'll live with it. We'll live with that approximation. And also, it's helpful to simplify. See, by saying, oh, I can take this complicated expression, C of Q plus 1, and subtract C of Q, and I can replace it with a simpler, hopefully, derivative of Q. Now, so that's how much it costs us to make one more. How much do we earn? Well, that's the marginal revenue. So it's the amount we earn by making one more, subtract the current amount, divide by 1. And again, same reasoning. We can say, well, that's about the derivative at Q. So when you hear the word marginal, marginal cost, marginal revenue, it says what happens on the very, very edge of what we're doing, and the moral is we can take the derivative. In some sense, it makes sense, because if you want to understand what's the behavior on the edge, it's like, how are we changing right at the end? And the way that we change, see that word change? That's a derivative. Change corresponds with derivatives. Now the question, when do we produce? Let's think about it. Suppose we're in this situation where C prime of Q is less than R prime of Q. What does that mean? Well, if we're thinking of the situation, this left-hand side, C prime of Q, that's how much it's costing us to make our next unit. R prime of Q is how much we're going to make. So it says that the amount it costs us to make something is less than how much money we're going to make. So it's like, wow, we should make that because we're going to come out ahead. The next one we make, we're going to overall make more money. So that says, hey, you should be increasing your quantity that you produce. So marginal cost, smaller than marginal revenue, make more. On the other hand, let's flip it around. Suppose marginal cost is above marginal revenue. Well, that says if you make another one, the cost of you making one more is going to be less than the amount of money you're going to get. So you're worse off making more. So if we're worse off making more, we should be pulling back. We should be like, whoa, we are doing too much here. Let's decrease. So we're going to decrease how much we make. So depending upon how the marginal cost and marginal revenue goes, if marginal cost is below marginal revenue, make more. If marginal cost is above marginal revenue, make less. And therefore there's that sweet spot. When they're the same, that says good. That says there's a place where there's no incentive to change Q because it's not clear whether you'll increase or decrease. So that's where you want to start setting your production levels. Figure out where that interchange happens. Now, be careful. We're going to talk about these types of applications of, what is the best. That's coming up in more of the application parts of derivatives, which is going to happen in the near future in upcoming sessions. Just because we're at a place where marginal cost and marginal revenue are the same does not mean, first, that we should produce, or second, that it's even in an optimal place to produce. We may have found the worst possible place to produce. But even if we have found the best possible place, it might be that if you look at the total cost versus the total revenue, it still doesn't make sense to produce. You can say, even in a best case scenario, I'm going to lose. And so you got to be careful. It's just not enough to be like, this one simple test works and we're done. You got to say, well, now let's probe and see, does it really make sense? Or do we need to reconsider our life choices that brought us here? All right, good. So now we have a little bit of applications. Isn't it nice to see how derivatives can connect to these wonderful things? Physics, economics, really many subjects now are connected because mathematics is the language of quantitative literacy, which is a very fancy way of saying with numbers. And a lot of things are more and more involved with numbers. All right, well, good. Let's start getting into some practice.